Yes, good morning, my dear friends, and also welcome to electronics online classes. As usual, we are discussing about the operation amplifier, and maybe, if possible, can complete today the operation amplifier because you have taken so much of classes, and because as you know already, you are having more weightage according to your syllabus, and also in general in electronics we are giving more importance to the operation amplifier. And as usual in the previous class, we are discussing about the so important property or so important application of the operation amplifier, that is how your operation amplifier can be used as a comparator. And maybe the today's lecture is about lecture number 12. We are going for lecture number 12. And as usual, we can refresh your knowledge and regain your knowledge what you have studied in the last class. Yes, in the yesterday's class, we were discussing about how your op-amp can be used as a comparator. And as usual, in your comparator, it is nothing but it is an basically it is an open loop configuration. Yesterday I said in detail about what is open loop and what is closed loop, and not necessary once again you say about that. And before that, we studied about the closed loop configuration of your op-amp. It means as usual the open loop and closed loop, but in open loop you are not applying any feedback, but in closed loop you are applying the feedback. And we are all completed the applications, linear applications of your op-amp. Also we have completed the non-linear applications of your operation amplifier, EPV, inverting amplifier, non-inverting amplifier, adder, subtractor, integrator, differentiator, or your logarithm, anti-logarithm. In everywhere you are using a feedback. You are using a negative feedback. And because you are using negative feedback and your gain, that depends only the feedback resistor and input resistors. But yesterday I said in your comparator you are not using any feedback. In your comparator you are not using any feedback. And that's what is called open loop configuration. Your comparator is also called as open loop configuration. It means in op-amp you are not using any feedback. And as usual, the comparator, it is a circuit. It is working on the principle of open loop configuration. And as their name indicates, it will compare the two signals. The comparator will compare the two signals. And the signal will be current or voltage. The output may be, or in your comparator, output indicates in this two input voltages which one is greater. In these two input voltages, which one is greater? That will show up by your output. It means the comparator, it is a circuit or device, they will compare the two voltages. In these two voltages, which one is greater? Which input is greater? That will give the output. And as usual, because you are using open loop configuration in your op-amp, and we know the open loop gain, ideally it is infinity for operation amplifier, but practically it is 10⁵. It means if you apply very small voltage as an input to your comparator or op-amp, you are having very more output voltage. But that more output voltage is not possible because as you know already, the output voltage should not more than the biasing voltage. That's why the output may be positive saturation or may be negative saturation depending upon your input voltages. And also you studied about the comparator having two types: inverting comparator, non-inverting comparator. In inverting comparator, you are applying input to the inverting terminal, and you are applying the non-inverting terminal as a reference voltage. But in non-inverting comparator, you are applying input to the inverting, and you are applying the reference voltage to the you are applying the input to the non-inverting terminal, and you are applying reference voltage to the inverting terminal. That is nothing but non-inverting comparator. And also, you already studied the most important applications of your comparator. By the comparator can convert analog into digital signals. By the comparator can convert analog into digital signals. It means if you apply the input as analog, we will get the output as digital. Because as we know already, the important thing is about in the output of a comparator, they may get only two values. It may be the output may be the positive saturation or the output may be the negative saturation. It means in your comparator, it is having only two outputs. The output may be positive saturation or output may be the negative saturation. That depends upon the input voltages, which in the input voltage which one is greater. It may be the V1 or V2 or V2 or V1. That depends upon that you get the output voltages. That's why I said about it is give the comparator give the digital output, because in digital I have two conditions. Here also I have the two conditions. It may be 1 or 0 or 1. That is nothing but the comparator. And also in your comparator you have studied about the two important applications, that is called zero crossing detector, and also studied about the schematic trigger. And zero crossing detector nothing but it is a type of comparator, and in this zero crossing detector you are applying the input to the non-inverting terminal. You are applying the input to the non-terminal and you are applying the reference voltage to the inverting terminal. And because in zero crossing detector what happens, whenever the input voltage crosses zero, the output changes. Why it is called zero crossing detector? The most important application comparator. The comparator is used as a zero crossing detector and schematic trigger. Zero crossing detector on the input, it is a type of comparator. In this comparator, whenever your input voltage is crosses zero, then the output will change. They may change positive saturation or they may change negative saturation. That's what is called as zero crossing detector. It means your op-amp can be used as a comparator, and comparator can be used as a zero crossing detector, and another one is the schematic trigger. The schematic trigger is so important because in schematic trigger it is also a type of comparator. But important thing, in schematic trigger you are applying the positive feedback. In schematic trigger you are applying the positive feedback. It means some of the output is given back to the non-inverting terminal. Yesterday we discussed already. I am not going in detail about that. In schematic trigger, the sum of the output is given back or given back to your non-inverting terminal. Sum of the output is given or is connected back to the non-inverting terminal. That's what is called the positive feedback. You are applying the feedback signal is applied to the positive terminal, or it is applied to the non-inverting terminal of your op-amp. That is called a schematic trigger. And important thing in schematic trigger, whatever you are given the input, but it will give the output as always the square wave. The input may be with the regular shape or irregular shape, but output always you are having the square wave. It means the important thing about schematic trigger is that they may ask the question, what is schematic trigger and how it works. Means the schematic trigger is basically a comparator, but you are using the positive feedback. And also the schematic trigger, whatever you given the input, the output may be always the square wave. And in this schematic trigger and zero crossing detector, we prefer the schematic trigger. Why you prefer schematic trigger? Because in schematic trigger you can reduce the noise. In your zero crossing detector, the output may changes because of the noise, but in your schematic trigger, the output does not changes because of noise. Whenever the noise is more than or equal to reference voltage, then only they may affect. If the noise voltage is less than B reference, positive reference or negative reference, then it does not affect. That is about the importance of your schematic trigger. And finally you go for the today's class about, this is about your studied in the last class, and now today you go for another one important applications of your comparator. And as I said in the last class, you have completed the digital analog converter, but in the remaining you want another one important thing, that is how you are converting analog into digital converter. Today you go for the analog to digital converters. Here in this analog digital converter, the important thing, it is called ADC, in short for ADC. And as I said already, in some cases we want in the output analog, in some cases we want in the output as a digital. It means in every electron device we are having the A to D converter, also we are having the D to A converter. Because depending upon the application, depending upon the user, sometimes we want analog signal, sometimes we want the digital signal. It may be the input or the output. And here to go further, how you are actually converting analog into digital conversion by using your operational amplifier. Especially you already studied about the DA converter. In the digital to analog converter, we are having two methods. One is called R2 ladder network, another is called your binary weighted resistance type of conversion. But here you are having the syllabus for the DDA converter, that is nothing but the counter type. That is nothing but the counter type. Counter type ADC. You are studying about the counter type ADC. It means while converting the analog and digital, you are using the counter. That's what is called counter type ADC. ADC is referred to analog and digital converter. And as usual, to construct an A to D converter ADC, it is having it requires the most important thing. It consists of a binary counter. It consists of a binary counter, and it also contains an D to A converter, and it also contains an comparator, and finally it contains an AND. These are the requirements to construct an analog digital converter, and it is nothing but counter type. It is having a binary counter, D to A converter, comparator, and AND gate. And if you draw the block diagram, and we can explain how actually can convert the analog into digital signal. That is important for by one question. And as usual, we can draw the figure, and actually the figure is very simple, and that figure actually here you are using an AND gate. I just said you are using an AND gate, and for one of the input for the AND gate is your clock signal. You are using a clock, and here you are using an I just said already, you are using an op amp. That is you are using an comparator, and here the output of the comparator is given to the input of your AND gate. Here you are having this output of the your AND gate is given to the N bit counter. It is having the N bit counter. N bit counter. And also we are applying a reset signal to the counter. And here digital output, and this digital output you are converting to the D2A converter. And here it will give the digital output LSD, MSD, and here you are having the digital output. And this actually this output of the output of the D2A converter is connected to the one of the terminal or here you apply an VA. You would apply another input signal. Apply another input signal. This is nothing but the maybe your V reference, and here having the AND gate and V reference, and this is about the simple block diagram of your DAC, gate to D converter. As usual, it contains an AND gate counter, it is having D2A converter, it is having a comparator and a AND gate. And important thing, how it works. What is the working principle, or how you are converting actually the analog into digital signals. And consider first we know about each block, how it works. As usual, we know about counter. Therein indicates it will count the clock pulses. The counter, the AND bit counter, it is a type of digital device, and it will count the clock pulses. We are studying, especially in digital electronics, how you are constructing the counter, how your counter works. You are studying in detail. But in brief here, the counter is a digital circuit, and in this counter, it will count the clock pulses. It will count the clock pulses. Whatever the input you are getting the clock pulses, that clock pulse will be counted by the counter. Whatever the input you are having clock pulses, that clock pulses will be counted by the counter. It means the counter basically counts the clock pulses. And as usual, we know clock nothing but it is in square wave. The clock nothing but it is in square wave. It is square wave signal. And as you know already about the construction and working of D2A converter. And whatever the counter will give the output, that output acts for the input for the D2A converter, and counter will give the output, that is in terms of digital. That digital you are applying to the D2A converter. This D2A converter, the digital input to the analog output. The digital input to the analog output. This analog output you are given to the comparator. And as usual, the comparator, we know already, the comparator compares the two signals. It may be this V reference and this VA. VA nothing but analog input voltage. These two voltages are compared, and in this which one is greater? As usual, you know the comparator. In comparator, the VA is more than VRF reference. The output will be, we may get the output is 1. If the VA is less than VRF reference, then the output will be 0. And it means the comparator compares the two signals. And if the comparator is given, the output is 1. This 1 here given to the AND gate, and always clock is 1 only. And 1 and 1, in that time your AND gate is 1. Because you know AND gate, when you get the, what is the principle of AND gate? Whenever both the inputs are high, then only you will get the output is high. If any one input is 0, the output will be 0 for the AND gate. This is in brief about each block of your A to D converter. And now you can take an example. You take the 3 volts. You take the analog inputs in 3 volts. This analog input 3 volts you are converting digital. You are converting. Take an example. You consider the 3 volts. You are applying the input to the non-inverting terminal of your comparator. We want this analog signal to the digital signal. And how we are converting 3 volts analog into the 3 volt digital. And initially, how it works means, initially because you are applying a reset signal or you are applying a clear signal to make it the counter 0. Initially the counter is not counting any pulses. Initially the counter is 0. To make it the counter clear, to make it counter 0, you are applying the reset signal. To make it the counter 0 or to make it the counter is not counting any clock pulses because you are applying the reset signal. To make it the counter 0 or to make it the counter clear. Then actually initially the counter is not counting any clock pulses because counter is 0. And it means if the counter is 0 means the output of the counter is for example it will be 0, 0, 0. Because we are applying the reset signal, that's why this counter is not counting any clock pulses. If it is not counting any clock pulses, the output of the counter is 0, 0. And this counter output is in terms of digital. This digital output acts for the input for the DDA converter. The digital output of your n-bit counter that acts for the input for the DDA converter. This DDA converter will convert this 0, 0, 0 digital input to the analog input, that is 0 volts. Right now, it means the DDA converter they convert this digital input to the analog output because your binary counter output acts for the input for the DDA converter, and this DDA converter will convert this 0, 0 digital into the analog 0 volts. And this 0 volts or you can say some reference volt you are giving to the inverting terminal of your comparator. And as usual the comparator compare the V reference and VA. And the condition is that the VA is greater than VRF, means the reference voltage. The input voltage is more than the reference voltage. Then what happens? Your comparator will the output as high. Your comparator will give the output as high because the 3 volt is more than 0 volt. The 3 volt is more than 0 volt. That's why the comparator will give the output as 1. This 1 you are giving to the as input for the output. And already because clock is 1, as usual, if the clock is 0, it is no use. Always clock should be then high, then only your digital circuit works. The digital circuit works whenever clock is 1. And also, as usual, I said AND gate. To make it AND gate enabled or to make it AND gate active, you have to apply both the inputs should be 1, 1. And you are applying both the inputs is 1, 1. It means your AND gate is enabled or it is active. They will give the clock pulses. Because the clock signal is given to the AND gate. And because AND gate is high, it means AND gate will give the clock pulses. AND gate will generate the clock pulses because your clock signal is given to the AND gate. The AND gate will give the clock pulses. This clock pulses acts for the input for the n-bit counter. This clock signal will generate the clock pulses. The clock generator will give you the clock pulses. This clock pulses will be entering into the n-bit counter. Or this clock pulse acts for the input for the n-bit counter and n-bit counter count this clock pulses. Because here only one count is there, one pulse is there, immediate at the output of the counter immediate 1. Because it counts the clock pulses. Here only one clock pulse is there, that the counter will count this clock pulse and in the output of the counter we make it 0, 0, 1. Once again, this 001 is in terms of digital. This you are giving to the as I input for the DDA converter, and DDA converter convert 001 the digital to analog, that becomes here 1 volt. And this 1 volt you are comparing with our input voltage. 1 volt is reference voltage, you are comparing with the VA nothing but analog input voltage. Once again here the 3 volt is more than 1 volt, that's why once again you are comparing because this condition, the comparator will give you the high. This high once again you are giving to the AND gate, and now always track is 1 only, and 1 and 1. Once again your AND gate is active or it is enable, you will get another one numbers. You will get another one numbers. You will get another one numbers. And now once again because the clock generator will give you the clock pulses. This clock pulses will be counted by the counter, because counter only but counts the clock pulses. Here you are having 2 clock pulses, means your counter is counting these 2 clock pulses, and you will get in the output maybe you get 1 0. Because you are applying 2 clock pulses, these 2 clock pulses counted by the counter, and output of the counter having the 0 0 1 0. And once again, this is in terms of digital. This output of n-bit counter acts as input for the DDR converter, and this DDR converter converts the digital input to the analog input. We may get 2 volts here. And once again, this 2 volts will compare with the 3 volts. And here also 3 volt is more than 2 volts. Once again, your comparator is high. And because comparator high means they will give you the one to the AND gate, and now also your the AND gate having both inputs are 1, you may get AND gate is active, you may get, they will give another one clock pulse. They will give another one clock pulse. Because whenever the AND gate is high, then only the clock pulses will enter into the n-bit counter. Now you are having the 3 clock pulses. These 3 clock pulses are counted by the counter, and output of the counter having the 3. How we can write 3? We can write in terms of digital 0 0 1. Okay, right? Because you are applying 3 clock pulses, that 3 clock pulses counted by the counter, output of the counter having the 3. This 3 is in terms of digital, and this digital output acts for the input for the analog to this acts for the input for DDA converter. It means once again they will convert digital input to the analog output. That becomes here in the 3 volts. And this 3 volts you are applying to the inverting terminal as a reference voltage. And here the condition fails because reference voltage and VA, the input voltage both are same. If your both voltages are same, as usual, the comparator will give you the output is 0. As you know about here, whenever the VA is nearly equal to VRF, we may get 0. Actually, here you can say about like that is good. You can write here phosphorus saturation. But when we will get the comparator will give the 0 output whenever the reference voltage and input voltage are same, because as you know already, the comparator is a basic op amp, and op amp is nothing but it is a differential amplifier. If the both input voltage are same, the output is 0. If both the input voltages are 0, the output is 0. That's why this 0 output of comparator is connected to the AND gate. And here we are connecting 0. And as usual, if any input of your AND gate is 0, the output will be 0. If any one of input is 0, the output will be 0. And it means it is not giving any clock pulses. It is not giving any clock pulses to the counter. It means your AND gate is disabled. Your AND gate is not active. It is not giving the clock pulses. And because your AND gate is not working, because your comparator is giving the 0 output signal, this 0 output signal you are applying disabled, it is inactive. That's why it's not giving the clock pulses, and that's why the counter also not counting this clock pulses. Whatever earlier the counter is counted, that clock pulses is as it is. Earlier having some clock pulses, that clock pulse will be retained as it is, and further it is not counting any clock pulses because your AND gate is not active. That's why this overall process stops here. And important thing, as I said here, you are applying the input 3 volts as analog, but you will get the output as this, that is 0, 1, 1. As we know already, the analog signal having 3 volts, that is you are converting to the digital as 0, 1, 1. This is 3 volts is analog input voltage, the 0, 0, 0, 1, that is in terms of digital. That is nothing but your output. It means by using the counter type analog to digital converter, you are applying the input as analog, but you will get the output as digital. Maybe example 0, 0, 1, 1. That is nothing but the simple working principle of your A to D converter. Actually, you are having an here the output of DA converter. You are having a staircase type of waveform. Output of the D to A converter, you are having the staircase type of waveform, or you are having some you are having the staircase type of waveform that you can write here. Actually, here you are having a diagram for that. You are having the staircase type of waveform. You are having the staircase type of waveform. That is your V0, and here you are having the counter. This is having the DAC volts, and especially as we know already about you are having the sounds. Consider 1, 2, 3, 4, 5. Count the pulses. This is about your analog signal. It means actually you are having an you can say here the output of the DDA converter, it is a type of staircase type, or is also called as stepwise. It is also called as stepwise signal. This signal acts for the reference voltage for the your comparator. This is about in brief about how actually we are converting analog into digital by the method of counter type. Because we are using an N-bit counter, that's what is called as counter type A to D converter. And important thing here is about we are giving more importance to the comparator, because the comparator and the application comparator is nothing but if you are applying the comparator input as analog, you will get the output as digital. And because as you know already, if you apply here another signal, because AND gate is a digital device, that's also we want comparator is here important also, because if you are giving this output to the as a input for the AND gate, and AND gate you want only the digital signals. That's why the comparator is important to convert analog to digital. This is about in brief about A to D converter. Now you are completing the theory part about your operational amplifier. Now you are having you will solve one or two problems, because as I said already, they will ask one question fix in your exam about 5 marks in operate, and actually according to your question cover pattern, you have to in that you are having choice, and especially in the part C. Sorry, we are having part D. You have to go for the problems, and in that you are having 5 problems. In that 5 problems, you have to solve minimum 3 problems. And one problem from already we have done that in transition amplifier. There is one problem. Next problem they will also go in our operational amplifier. And third problem we are going for your discussion afterwards, that is oscillator. Remaining the two problems from digital electronics and communication. Means now the important thing about we will solve some problems on your operational amplifier. We will solve the problems on operational amplifier. Because in exam the one problem is fixed, that is 5 marks. And you are already having your study in detail about the problems on operational amplifier. We will solve one or two problems, and especially you take the problems which are asked in your question paper, or what type of question they asked in your every year in the annual exam. You take first important question. This question asked in your last exam, that is 2020 March, and you have to calculate the output voltage. Calculate the problem number 1. Calculate the output voltage. If the below circuit diagram, the condition they are given, if they are given the condition, if V1 equal to 300 millivolts and V2 equal to 700 millivolts, they are given the inputs. This question asked in the March 2020, March 2020, asked in March 2007. The two times same question asked, and they are given the diagram. You can write the diagram. You can go for there. It is having an consists of an inverting amplifier. As usual, in inverting amplifier, make it non-inverting terminal grounded, and you are applying a feedback resistance. This is nothing but your output. You can apply plus 12 volts, minus 12 volts, and you are applying an input. Like an input here, that is nothing but your V1. The V1 already given, and the value is 50 K, and this is your 500 K, and this output acts for the input for the next. And you can consider this both the inputs X for the here here they may apply 100k. This is also 50k, and here having then 500k. We want the output voltage, that is plus 12 volts minus 12 volts. And you have to find out the output voltage. It's simple, as usual. It is your inverting amplifier, or you can consider this your A1. This is nothing but A2. E1 nothing but operational power, A2 nothing operational power 2, and the first your A1 acts as an inverting amplifier, and we know the voltage in for inverting amplifier, and after finding the output voltage of your inverting amplifier, this output voltage acts for the input for the second A2, and here by seeing your A2, it is nothing but an adder. The A2 is nothing but adder, because you are applying the two voltages. You are applying two voltages to the inverting terminal, and non-inverting terminal is grounded. It acts as an adder. The solution, we go for the solution. The first thing, important thing, the A1, your A1 acts as an inverting amplifier. Your A1 acts as an inverting amplifier. It means we know the output voltage in inverting amplifier, V0 equal to minus RF by RI, or can say R1 into VI. And as usual, we know the RF and RI because of the here. We may get RF equal to minus how much it is 500 K divided by 250 K into can apply the V1 is how much 300 millivolts. 300 into 10 to the minus 3 volts. Then we can 250 over the 250 closer. We may get minus 2 into 300. Or we will get 6 minus 600 millivolts. We may get 600 millivolts. This is the output of your inverting amplifier, and this output acts for the input for the adder. Then, as you know about adder, right here. The for your output voltage for the adder, that is we know the formula, minus RF by R1 into V1 plus RF by R2 into V2. Use this formula, and you want to take don't confuse to take minus sign here also, because the minus sign is common for both. Don't confuse. Then you substitute the RF value. How much RF? That is 500k. 500k by R1 100k, and into minus n as it is, into how much for output? The output that is 600. This also minus 600 millivolts. Then this minus n as it is. Here also RF by RF 500 by how much? 50 K as it is, 50 as it is, and into how much you are into having the V2 is almost 700 millivolts. Very simple. We can simplify this as we can get 100 is 2 is cancel, and 50 1 intention. We make it here and continue here. And yes, we make it output here. This is what we get output. The V0 equal to here we may get 5 minus 5, and how we can write 600 millivolts? You can write minus 5. You can write 600 millivolts. You can write 600 millivolts. You can write 0.6 volts. You can multiply by minus 0.6. Then minus as it is. Here 51 and 50 tens are 10 into 0.7. And write 10 into 0.7. Can write 10 into 0.7. And because 51 is 10 feet. Then if we get here, just simplify minus into minus plus 5 into 0.6, we get 3. And here minus 10 into 0.7, we get 7. 7 minus 3, or we get the output is nothing but V out is equal to minus 4 volts. That is the final answer, very simple. And because here minus into minus plus 5 into 0.6 is 3, and 10 into 0.7 is 7, and 3 minus 7, we may get 4 volts. This is very simple about the problem. The important thing you have to see the A1 is what and A2 is what. Because A1 is acts as an inverting amplifier, and we know the A1 acts as an inverting amplifier, and we know the voltage gain for inverting amplifier. V0 equal to minus RF by R1 or Ri into Vi, and RF is 500 and Ri is 250 into 300, and they will cancel. You get 250, 250, you get minus 2, 300 as it is, and 3 into 300 will make it 600 millivolts output. And here this output acts for the input for your adder, because you are applying 2 voltages. You are applying 2 voltages. These 2 voltages will be added and you get across the output. And it means your A2 acts as adder. For the adder, we know the formula RF by R1 into V1 minus RF by R2 into V2, and we know RF and R1 can substitute, and because here V1 nothing but this output, that is V1, and here minus because you are taken minus sign inside minus, and here RF by R1 as it is, and V2 we take it 700, and you can simplify, we get minus 4 volts. This is also one important problem, and it is very simple. You can go through once again. And now we can go for another problem. We go for another problem. This problem also asked in the exam. This problem also asked in the exam. And we go for that. The second problem that also asked in the exam. That is nothing but small change here. Yes, this also very simple, but they have changed the values. You can write problem or you can write very simple. Find the output voltage. Find the output voltage. In the below diagram, I am not writing everything because there is so much of time, and they have given the diagram. It also consists of the same. It is repeated, no problem. But only they change the data. But important this question asked in the exam. That's why I am going for this. This is once again you are connecting and you are using an inverting amplifier. You can apply the feedback resistor. And you can apply an input voltage. That is nothing but they are given the 300. They are given the change the V1. That is 300. this is nothing but your V2. That is also they given about 200 millivolts. And this is like to the as inverting terminal and non-inverting is grounded. And here it is also the non-inverting terminal is grounded. And the important thing is about this values 10K and 47K remaining about as usual this is your plus 12 volts minus 12 volts, here also plus 12 volts and minus 12 volts, and here below. And as usual can find out voltage here. As I said already, very simple. Your first is nothing but your A1 and right solution. A1 is inverting op-amp, and your A2 here, your this is nothing but A2. Our A1 acts as a inverting amplifier, and we know that it is gain our voltage, that is 0. The output voltage is nothing but minus Rf by Ri into the Ri. And here Rf is 2.2K, 2.2K by 1K, and into how much they given 300 minus is minus 300 millivolts. And we can simplify it, we may get here. Yes, 2.2 divided by 1 is 2.2 into we may get V0 equal to 2 minus 2.2 into 300. Or you can write 0.3. You can write minus 2.2 into 0.3. We may get answer. We may get about 600 or 0.66. Or you can write minus 660 millivolts. This is about V01. Very simple, you can use the formula and you can substitute the values as you are perfect. Use your calculator because it is allowed in your exam, and you can simplify it. We may get V01 660. The change is about their changes resistance. It is as similar to another first problem. Then now once again your A2 is used as a summing amplifier or adder. The second is A2 is your adder as a adder. Then once again we know the output voltage of the adder, that is you take Rf by R1 minus the you take common V1 and you take plus Rf by R2 into the formula, and don't take minus sign inside. V0 equal to minus R by R1 V1 plus minus into plus minus R by R2 into V2. Now you substitute the RF value, that is 47K by R1 is how much? 10K, and V1 how much it is? Minus 660. You can write here, already minus is there. Once you are getting minus 660 millivolts. minus. Here RF is once again 47 and this R1 is 10K and into they are given this V2, that is 200 millivolts. You can simplify it, you may get nearly about 47 by 10 nothing but 4.7, and here you may get 0.66 minus 4.7 and minus 0.66 minus here you may get 4.7 into 0.2. You can simplify it, you may get minus into minus plus 4.7 into 0.6, you may get 3.10, and here minus that is 4.7 into 0.2, we may get nearly about 0.94. Then the output voltage is very simple, we may get 2.16 volts. This is about very simple to calculate the output voltage, because as I said it is your inverting amplifier, this is adder, and we know about the output voltage in inverting amplifier minus Ri into Vi, and we can substitute here and we will get the value here. This is the output of inverting, this output acts for the input for the second unit. This is about the second problem, and we go for another problem that also I think this is very different problem. Take the different problem. As compared to the physics or chemistry or in electronics, the problems are very simple. But only thing you have to remember the formula. Find the output voltage as given below diagram is common. You take the small change in the diagram. Once again, you are using an inverting. You are using an inverting amplifier. And here we are connecting an and this value is about 3K and this value is about 6K and 2 volt plus 12 volts minus 2 volts plus 2 volts minus 4 volts. This both the outputs you are connecting to the another one. This both the here but without condition. Say plus 12 volts minus 2 volts and you are applying the 2k. It's very simple. 2k, 1k and this also 1k. Yes, so here load consists for A1, this is A2 and this is for A3. Now as usual we have about the A1, A2 and A1 is about inverting amplifier, A2 nothing but non-inverting amplifier and here the A1 and A2 outputs has the input for the A3 and your A3 acts as subtractor. The A3 acts as a subtractor because you are applying A1 and B2. We are using inverting as another department. That is about the expression and you can go for the solution. You can go for solution here only. Solution for your A1 is yes applying the inverting current. It is inverting current. I am not going in detail because already you are familiar. Because we want output is nothing but minus and minus Ri by Ri into Vi and here your Rf is about 4k by 2k minus the as it is and you are applying one model. Very simple. The immediate output is how much? 2 volts. The output is about 2 volts. Minus 4 is minus and minus 2 volts. Or can write here the out is equal to minus 2 volts. Then you go for the this is nothing but A2. Your A2 is non-inverting operator. Your second one, that is you can write V02, that is nothing but 1 plus Rf by R1 Ri into Di and substitute the values. 1 plus yes, how much we are applying Rf? That is 6k by 3k. 6k by 3k and into how much our input? That is 2 volts. Input will be 2 volts. You can simplify it. You may get 2 1 3 1 3 2 and 2 plus 1 3 into 2 minus. You may get V0 equal to minus 6 volts. Yes, sorry, we are getting minus. Here V0 equal to 3 into 2. That is V0 equal to 6 volts. Now, as usual, these two outputs acts for the input for the subtractor. And we know the subtractor formula. Your A3 is subtractor. And we know the formula for subtractor, that is V0 equal to minus Rf by R1 into V01 plus, you can write about 1 plus Rf by R1 into R3, this is R3 divided by R2 plus R2 into as usual V0. Just simplify it. We may get V0 equal to this. You can go ahead. Very simple step because here RF by RI nothing but 1K. Here your RF nothing but 1K by 2K, because here your this is RF 1K and 2K. You can write here minus RF is on 1K by 2K, and into how much you are applying, how much you are getting the output, minus 2 plus here 1 plus RF is how much, your RF is about 1K by 2K, and here into RF is how much again, 1K plus this 2K and 1K, 2K and 1K, 1K divided by 2K plus 1K, 2K plus 1K, and into here your output voltage is how much, output voltage maybe output voltage is about 0 to 6 volts, 6 volts, and you can simplify it, you may get the output voltage nearly about the output voltage about 4 volts. You can simplify it, you may get the 4 volts. This is about very simple calculation about the, because you are using here inverting amplifier, non-inverting amplifier. We know the voltage gain for inverting and non-inverting amplifier. This both the outputs acts for the input power subtractor, and we know the power of the subtractor, and you can substitute the values in the simplifier. Finally, they get the output voltage near about V0 is equal to 4 volts. This is the important problem they will ask you in the exam. And if not, you can try your home about another one simple problem. You can go for that. Can do it in home. That is very simple. You can go for another problem. You can go for, take it as homework. Take it as a homework. Very simple. Same, find the output voltage, and it may be the fourth problem. And it is very simple. Minus plus, and there. You are applying your input here. Input voltage is in what V1 3 volts and 10K, and here this output very simple. You have to calculate. It is your inverting amplifier, it is your buffer amplifier, or it is your voltage power. And very simple, you have to find out the solution. Sometimes they ask 2 mark question about here the output is nothing but minus RF by R1 into PI, and here RF is almost 10K by 10K is by 10K, and into VI is about 3 volts, and the minus, both will cancel. is about minus 3 volts. The important thing is V01. This output acts for the input for the second, and it may be your A1, this is your A2. And here the important thing is about because it is buffer amplifier, whatever the output that follows the input. That's why the overall output is nothing but minus 3 volts. Because you are using an buffer amplifier, you are using a buffer amplifier. That's why it is nothing but whatever the output, same for this output. Because you are using a buffer amplifier, for buffer amplifier, the output follows the input. The output follows the input. Whatever the input here, the minus 3 volts. This input acts for the output, but this also minus 3 volts. This is about in simple problems on your operation amplifier, and maybe you have completed the operation amplifier. And in the next class, you will start a new topic that is about oscillator. Thank you.